I spent a year.
So Valerie was saying there were quite a few people over in the science
No, I said you just use the word. Why isn't chemistry?
Oh, this is actually where I teach before I teach your class.
Is that the big bang class?
Sure. It's actually usually pretty useful.
Yeah. What is it technically?
So that class has 150 students in it. But actually, the first day that we had class was also the day of the big technical side of the skills. So that day I had 7 empty seats. And the seats were easy stuff.
So how many what kind of class is it?
Oh, so that's a sort of large distribution introductory class. We're not majors, but if you're a major, you can do it. I think someone in your classes. You could literally just have these one.
You know, this I think they should build a third science. They get clear glass opens.
Well, so I just need to use that. But we're talking about how this size building yeah, something that
It's actually put in order.
what I'm saying is. Okay, my personal one, you have to sort
Yeah. Or they're just like. But it's weird. It should be costing us to get anyway. So then, yeah. So they changed our bill. I used to hate cats.
No.
I remember Joseph says I thought I saw you after that question.
It's all right, Dad.
Except that awkward silence, the room just kind of hushed down.
Oh.
Another minute, let me check and make sure no one's on.
Sure thing. Yeah, we'll get started in probably about 2 minutes. So. I think I shouldn't. I would use words. Sorry about that. I left Oh, that was the wrong one. How's that? Perfect. Awesome. Awesome. Well, welcome to SUNY Oneonta, everyone. There's a lot of people that I recognize from the movie and outside, and thanks for coming. This is going to be a great talk. My name is Josh Mullenberg. I'm one of the two astronomers. Valerie Ross is another astronomer on campus as well. And the Department of Physics and Astronomy would really like to welcome you here. A couple of things. In addition to talks like this, we also do planetarium shows every other week. So feel free to check us out on Eventbrite by going to the Science Discovery Center Eventbrite page. And the next show will be next week. And each one is different, each one is live. And all you have to do is register for free tickets to make sure that you have a seat. But for tonight, what we're going to be doing is talking about, we're going to have a talk by one of our former students, Mike Engesser, graduated in 2017. He was one of my first students on campus here. And it's really great that he can come and actually talk about what he's doing on the James Webb Space Telescope. Back when he was a student, he worked on a variety of research projects. We went to San Diego at one point for a AAS meeting, and he decided to go there for graduate school as well. While he was there, it was actually a really amazing conference. I remember we were sitting in a panel discussion on the future of cosmology, the study of the evolution of the universe. And there was a big panel of very, very prominent astrophysicists, James Peebles, who now has the Nobel Prize, Joseph Silk, Virginia Trimble, Sean Carroll. It's actually a really huge sort of community event in the astronomical community. And Mike Engesser actually walked up to the microphone, asked a great question, which caused a couple of panel members to stop and sit down next to us, sort of during the intermission time to talk to us. It's actually a really great experience. Since graduating with a master's degree at San Diego State, he's actually moved on to the Space Telescope Science Institute, where he's working as a staff scientist with the James Webb Space Telescope, which you may have heard in the news lately. Welcome to SUNY Oneonta once again, and Mike, I'll give you the floor.
Thank you for having me. This is surreal. This was the room I took my first intro-level astronomy course at Oneonta in like 2013. So this is special places. So I'm very excited to be here. This is a great honor. And I'm happy to talk to you all about James Webb, which has been in the news a lot recently, so I'm sure you have any questions. But maybe you don't, because you don't know what that is. So maybe a show of hands if you know what the James Webb Space Telescope is, or did you know when you started it? No. Some people know. Do you know what the Hubble Space Telescope is? Yes. Okay. That fills in the holes. So James Webb is a lot like the Hubble Space Telescope. It's in space. whereas Hubble is in orbit around the Earth, James Webb is in orbit around the Sun in a very complicated orbit that keeps it very stationary relative to Earth. It needs to be there because it's not an optical telescope like Hubble. Hubble sees the light that we see with our eyes. James Webb is an infrared telescope, which means it sees what we generally consider but much further out in the infrared. And that's good because it's great for a lot of really, really interesting and important science cases, you know, cosmology and Big Bang, as well as looking for exoplanets that might harbor life. So it's a super big deal, and it's been in the works for 30 years. The project is older than I am. And it finally launched this past Christmas. And just finished commissioning this summer, and some of these pictures you'll see at the end here, it's released, you've probably seen them. I think you're using them on your planetarium advertisements. So we're going to talk about all that stuff, but this talk, I think what I wanted to do was, for those of you that are familiar with James Webb, you've probably heard ad nauseum about its history and what it's for and what it's going to do. Great. What I wanted to do here was take a look at some of those things, but also just at the process of commissioning the telescope once it got to space, what that was like, the things we weren't allowed to tell the public as they were happening because NASA has very tight-lipped. We'll talk about some of the really interesting things about the project, and then we'll get down to the pictures and the science and some of the good things that are already starting to happen. So that was more or less my intro slide. So, like I said, we launched on Christmas last year, which was a little bit annoying because it had been scheduled for the spring, and then it got pushed into the fall in October. And so for commissioning, this is, by the way, commissioning team for development. Is very nice. We have to staff what's called the Mission Operations Center, which is based at the Space Telescope Science Institute. Cool place. It's very much like you see in the movies. There's lots of monitors, there's people sitting around talking about headsets. Commissioning officially starts 12 hours before launch. So someone has to be there 12 hours before launch. And leading up to it, it kept getting delayed because of weather, because of, you know, there's an issue on the launch site, the clamp band. And as it started happening, we were like, oh, it's going to launch on Christmas. So Christmas Eve, guess who has the ship that starts 12 hours before launch? This guy right here. So very interesting, not ideal because I wish I could have stayed home. But so this is the cafe in the Space Telescope Science Institute. It does not look like this normally. This was the Space Telescope Science Institute being very nice to us, giving us a 5-course catered meal on individual tables. These tables don't normally have tablecloths, and now they do. And I have no idea who any of these people are, because there were so many people in from out of town, from Ball Aerospace, from Goddard Space Flight Center, from Raytheon, from CISA. So it was fun, but also a little bit awkward because none of us knew what was going on. And it was Christmas Eve. But launch was coming up. I went home. The next day it launched. This is weeks later now. So it got to space just fine. This is what it looks like inside the Mission Operations Center. This is me. You can see we have all these big monitors, and a lot of what we're looking at, you might think we're looking at images and stuff. No, it's just numbers, lots and lots of numbers. And making sure those numbers are green and not red, because if they're red, that's bad. And I'm writing a little bit of code here to do some analysis. So that's a lot of what commissioning was. We also have, we did have like a 3D tool where we can vision the telescope and what it looks like and what it's pointing at, just based on these telemetry numbers. But other than that, it's a lot of sitting around. So James Webb is, it was tricky to begin with because it's such a big telescope for what it has to do that it would never fit in a normal rocket. So part of what had to happen was it had to be deployed, sort of like reverse origami. So it's folded up and you have to unfold it. Hopefully it all works. And that's very tricky. So this is a short video showing the entire deployment process, about 2 minutes. I'll describe some of this stuff as we go. So it gets there to space. That's great. It's 31 minutes. The solar panel deploys. So I'll talk about that more in a second. That's how it gets its power. It's solar powered. And then it has, you see these sun shield pallets come down. It has to block out the sun because it's infrared light. The sun's hot. So we really don't want the hotness affecting our ability to see things in infrared. So we have to block it with this giant shield. With the shield, each layer of the shield, it's 5 layers, is less than the thickness of a human hair. very delicate. So unfolding, putting this on a rocket, which is basically shaking it around, you know, 20 minutes, something like that. And then you have to get there and unfold it without all the cables tangling up. And there's 700 points of failure. It was actually something. Single points of failure. If that one thing went wrong, the whole mission was wrong. So this was a lot of it. This was what everyone was stressed about when we first started. So this whole process took about 14 days, and then the alignment of the optics took about a month total. So that put us well into January at that point. That there is the secondary mirror coming down, and that doesn't come down. The telescope is just the way it works. So I'll let this finish playing out, but you can understand why this would be very stressful and why people would be engaged, the public would be engaged in wanting to know what's going on if something went wrong. This is the actual telescope just after it's bringing this rocket all the way to space from the coast of French Guiana. This is the view we got. This is from the launch vehicle's camera pointing at the observatory, just as it released. Of course, this is 8 a.m. on Christmas morning, and we're all pinching our fists. It's I mean, it's gorgeous looking. It's very shiny. It has to reflect the light of the sun. But I want to point out one thing that happens here that is starting with lots of questions. Now, the launch went really well. If you watch the video, you can hear the launch manager. Sorry, but he kept saying the word "coming out." It's going correctly. That's what we expect. So we're all thinking, okay, it's going great. And we knew that after the launch, it separates from the launch vehicle here, and we're expecting the solar array here to deploy. We weren't expecting to see it on camera, but if you have watched this array, you know that we end up getting to see it deploy. There it is. However, people that were very interested in James Webb had studied the launch videos, and they knew that this was early. This happened earlier than the launch video said it was going to happen. And so initially, Twitter was not racing. These are actually some fairly well known. I'm a rationalist. It was obvious it didn't work. Not sure why it happened early. Scared me. Notably different. Yeah. Okay. And this is going to happen the entire length of the mission. But the truth is, it actually went perfectly. The launch was so good. So the telescope is monitoring telemetry. It's monitoring how far it is from the launch vehicle, and it knows when it's safe to deploy the solar array. As soon as it's safe, it'll deploy it. So a perfect launch gets you to the point where it deploys it early like it did. However, when NASA publicizes its expectations, it doesn't give you the best case, it gives you the super worst case. So people were surprised it came out so early, and they thought that meant that there was a problem. Here was an actual problem, potential problem, that the public didn't get to hear about right away, because we were told not to tell anybody, obviously. So part of the deployment process, and this is on New Year's Eve at this point, is these pallets come down that hold the solar array, and they're wrapped up in these covers, protect them from dust and stuff. And they need to, they're rolled over the top here, as you can see. They unroll. And the unroll is just basically like the tension. If you've ever had wrapping paper and you unroll it, it wants to roll itself back up. That's how this is meant to work. It wants to roll itself over the edge, at least it's the solar shield can come out. The problem is one of these, we have a telemetry, a sensor basically that's supposed to tell us if it's successfully rolled over. It didn't say. It press the button that said, okay, roll over now, and it didn't happen. Which is obviously scary, because now you're thinking, well, now we can't unfold half of our sunshine, which is a big problem for this telescope. It turns out that it was totally fine. What they did was, well, NASA are actually quite smart. They could measure the temperature on the opposites, well, all along this ridge here, there's temperature sensors. There's temperature sensors everywhere, and a number of other sensors. And they could tell by looking at the temperature as a function of time when this happened, that it changed in such a way that indicated that the shield had in fact rolled off. And so, though the telemetry was telling us patterns that we shouldn't proceed, it proceeded anyway, and it worked. So that's one of the deployment scares we had early on. This is another thing that you probably heard about much later than it actually happened. Space is full of things. You might think space is empty. It's not. It's full of tiny little things. A lot of those things are called micrometeorites, and they're moving very fast, even though they're very tiny, and they impart a lot of energy. There was an expectation before launch that we would encounter micrometeorites hitting the telescope a couple times a year. It happens to everything that's in space. You know that's going to happen. So we can plan for that. There was one that was a little bit bigger than we anticipated, and it happened a tiny bit more often than was anticipated. But it's nothing to worry about. These things are so tiny that they change the actual waveform error, or how we measure how focused the observatory is, by tiny amounts. You notice that the scale here is in nanometers. So this pre-launch scale shows not very much change, and you can see that the micrometeor right here, you can actually tell what direction it came from by looking at telemetry from the telescope, which way it tilted, and how the waveform error changed. It's positive or negative. So obviously, we didn't tell the public that because they hear micrometeor hit JWST and they thought the whole thing was so that's a lot of the engineering and deployment process. A lot of the time for us, so I'm part of the vision for an instrument team. We work on vision for an instrument, basically a camera. So I'm not very involved in the deployment process. Basically, we just get to sit there and listen and pray. What we do, the instrument scientists on all of the science instrument teams, we do these things called PARs and CAPs. PARs and CAPs are commissioning activity requests. Commissioning analysis projects is basically saying you want to go observe something in space or some kind of test, which requires specific computers and some commands to the observatory. And then the CAPs is when we take that data down and analyze it to figure out what's going on. So we do this because we want to characterize the observatory performance, define best practices for observers going forward, and to generate important reference files. These are things you can use to process your data later on using the data pipeline. We want to have all this stuff available by the time the data goes public. That's the stuff we do during commissioning. Example of these things we do, we take dark exposures. So the telescope cameras on astronomy, when we use cameras like a CCD or a mini like this, the camera has some base level of charge. And that base level of charge can be pretty high depending on how hot the instrument is. And that's not something that's in space. It's not something you're seeing that's real. It's part of the electronics. So we can measure that by just keeping the shutter closed, taking an image and subtracting that off later. And that's sort of the process that we do for all kinds of things. Flat fields, nonlinearity, which is how the detector behaves as it collects photons. Stray light is light that's bouncing around in the optics in ways that you don't expect, and then it's up on your detector, and you're like, how did that get there? Latency is when you have a really bright object that you take a picture of, and then take another picture later on, and it's still there. Then we have to test things like target acquisition, which is looking at a star and trying to figure out how best to put it in a specific pixel on the detector. This is useful for things like pornography. Masking, you need to be able to put stars very accurately behind certain masks to block out their light so that we can see exoplanets. And moving target tracking, you might notice that you might have heard this weekend that we successfully crashed something into an asteroid. James Webb was actually able to track that asteroid as it was moving, which is not something it was designed to do that fast, but it found that it was actually capable of moving that fast. So these activities produce a lot of data and data that the instrument scientists then have to go through and determine what to do with, how best to handle. So I thought what I would do here is show some of the effects, the detector effects, stray light effects, things like that, that are not pretty but have fun names, that you'll never see in the data that you see that's getting publicized, because these things are corrected for in the pipeline before you ever get the data, which is the goal of commissioning. So we'll just look at a couple of these fun ones. NIRCam has something called dragon's breath. This is some kind of stray light feature. There's not much about it other than it has a full name. They actually also have a dragon's breath too, and it's just sort of like NIRCam is coming up with escape quests at this point. They also have claws and wisps, which are more stray light things. They're very cool looking, but they're not astronomy. This has an effect. This is very strange, but it's only ever happened once. We call it the ginkgo. You have this off-screen star here, and you have the diffraction spikes. These are normal, but then there's this weird shell shape or leaf shape that if you revisit that spot, it's not there, which is strange. But it's not an astronomical object, it's some kind of detector effect. NIRCam also has what they call tacticals. So this image, you might not look at this and think very much like it looks like space, but what this is called slitless spectroscopy. So these are all spectra. This when you take the light, kind of like the Floyd logo, you get a ring go out, you do the same thing with infrared light. And when you don't only look at one star, you look at all the stars in the image, and you look at all of them, you get this very fun thing where there's tons of stripes. This is real astronomy, but this is a weird effect that they call the tactical here. Somehow. NIRISS, the near infrared imagery and spectrograph, has what's called ghosts. And this is fascinating because I don't know how this happens. And I don't think computers people do either, but they found a way to correct for it. You'll notice that it's much clearer in this picture here. All these pictures are from the JWST Docs website, by the way. You can go and find these and read about them. You'll notice that there's the exact same pair of objects in several spots at different brightnesses. And they all have to do with some center source. And this isn't gravitational lensing where you have some massive group of galaxies that's literally warping the light as it goes through it. You can get multiple images of galaxies in the background. This is something else. This is a non-desired effect. So another thing that the teams have to deal with. NIRISS has what's called a lightsaber. This is not a diffraction spike from a star that's off screen. This is something that, again, is some kind of stray light that they don't have the source of. Now, all of the near infrared instruments have what's called snowballs. If you've ever heard of cosmic ray is a particle that's flying through space from the universe. It's got a ton of speed, a ton of energy. When it hits the detector, it gives off maybe something that looks like this. It's just a little bright spot. It doesn't have a point spread function like a real point source would. Sometimes they look like streaks because they hit the detector and sun. So those aren't stars. We don't want those in our images. This is sort of the same thing. In fact, in the sense that as you're exposing, it pops up suddenly in one frame that it wasn't there before. But it's thought that this is caused by alpha decay in the detector itself. So the detector is made of some silicon material, and it's thought that you have some kind of radioactive decay spontaneously, and it happens pretty frequently actually, that just imparts a ton of energy in the detector all at once. So you get these round, perfectly round snowball shapes everywhere in near infrared instruments, and it has to do with the material that the instruments are actually made of. Detectors are actually made of. So these are definitely a pain in the butt for the near infrared instrument. Luckily, the mid infrared instrument doesn't have that, but we have something interesting about it. It's called glow sticks. So this is a scattered light effect, something that we really see on the ground, where along these on the top and bottom edges and around coronagraph bits here, especially on the horizontal axis of these coronagraphs here, you have these bright bars that really should be there. So the mid-infrared instrument context, this is the imager detector, this is the imager field of view, and then we have this mask here that contains 4 coronagraphs. And what these do is block out light from the star, as I said earlier, so that you can see an exoplanet or some kind of green disk orbiting, which is very cool. It's easy to see how that would work with this. It's got a big black spot that you can put a star behind. These is a little bit trickier to explain. These are called 4-quadrant phase masks. Basically, what they're doing is they're uneven bits of glass that introduce a phase offset to the light. This is complicated optics. I don't expect you to understand. But basically, the light cancels itself out if you put the star perfectly behind the very middle of the crosshair. It's not easy to do. You need about 5 milli-arcsecond accuracy pointing, which James Webb can do. The problem is you need to know what pixel is exactly behind the mask. And that can change after launch because the whole thing shakes around and the mask might shake differently than the detector does. So we have to recalculate where the centers of the chronographs are. The problem is these stray light features make that really hard using the algorithm method. So if you ever want to use these chronographs, you have to find a way to get rid of it. And I'm very close to the person who figured it out and they deserve all the credit for it. But basically what you can do, this is just an example of what it looked like on the ground versus like what we got in space. So this was obviously not a good surprise for us. But what you can do is observe what's called a reference star, a star that looks like the one you're interested in, but doesn't have anything around it. So you take an image of that, the one we care about, and subtract them, which is useful. You can also do angular differential imaging, where you rotate the telescope on an axis so that the star is slightly misaligned, but most of it is still in the same spot. Or you can take a dedicated background observation and something that you can subtract off. So this it ended up being sort of a pain to come up with ways to tell astronomers how to use the telescope. They had to add time to their programs, which would be expensive. But they once figured out how to fix it. So now aside, we've fixed all those things. It's good. You never had to see, but that's what commissioning was for. And you end up with images like this. So this is the Carina Nebula from the early release observations that we did with James Webb earlier this summer. And it's beautiful. This is a huge mosaic of the Carina Nebula. So what they do here is the detectors they can't see something this big. What you do is you take images of small regions of it, and then you move, you take another small region that overlaps, and you keep doing that with all different filters and all the different detectors, and then you can combine them all together using the pipeline, and then add all the colors together, and there's a lot more that goes into these particular pictures because they're so publicly facing. But then you get a really beautiful thing. So even in a picture like this, where we're not aiming to do science, we're just aiming to do something pretty, James Webb is seeing all kinds of great stuff. For example, stars are things that were never seen before. Because James Webb is an infrared telescope, we can see through all the gas and dust, the stars that are hiding inside it. It's cool because those stars are just being formed of stars. You can see that contrast between this orange bit and this blue bit here is because there's a ton of really bright young stars, huge stars that are blowing off all their mass, or giving off a ton of radiation, and it's pushing against this cloud of gas and dust here. So it creates this sort of hole in the nebula. You can see that in some cases, you end up with these kind of pillars. There's so much pressure coming down from that direction that the gas is blowing around. But this is a really, really dense pillar. There's probably a protostar in there, but we can't see it because of how dense gas is. So there's all types of really interesting science even behind these pictures. This is another one of the early release observations. This is the Stebbins Quintet. This one's got a ton of really interesting stuff in it. You might have heard the phrase going around that every James Webb field is a deep field. the Hubble Space Telescope, early in its tenure, pointed at what appeared to be a blank spot of sky for 10 days, just to see what was there, which is a bit controversial before it happened. But if you recall, it was an amazing thing with tons of galaxies and it kind of changed how we view the universe. We sort of get that by accident with every image we take of JFST. That's how powerful it is. So this is Stephan's quintet. We're really just looking at these foreground galaxies here. Every dot back here is a galaxy, very far away. They're all quite red. So you're very old, very far, very dusty. But even here, so this is a near camera near composite, so near infrared and mid-infrared. Mid-infrared is very good at looking at dust. So you can see big dust lanes surrounding this galaxy in the center here. They're a little bit bluer. These are two galaxies that are sort of merging. You can see there's not a whole lot of dust in between as they're interacting. It's blowing out the sides like this. This galaxy has dust in the middle of it. This galaxy, you don't see really any dust at all. It might be quite cool. It's a very small spiral galaxy back here. And then this galaxy is actually much closer. You can't tell that just from looking at the image, but it's actually just the vantage point playing tricks on you. If you get the high resolution of this image, you can see so many individual stars here. It's really quite incredible, mixed in with all the gas and dust. This is the, I'm just going through all these observations here, but just in case you hadn't seen it, this is the Southern Ring Nebula. So this is what they call a planetary nebula, which is really forming for it because there's no planets involved. This is the aftermath of the death of a fairly young star or fairly old star, which just sort of expels its outer layer of gas, commonly leaves white dwarf behind. And you can see in this image that there's a bright star at the center here, and it's there's a lot of really ionized gas, really energetic gas here. That's again blowing, exerting pressure on this outer nebula. So there's this kind of encased cell. And in the mirror image, you can see that there's actually two sources here, which is something that I don't think we knew before. And you can see even more the sort of wind blowing on the nebula from the inside. And one interesting thing that we found when we were looking at this, and there was a lot of debate about what this was, is if you see this object here, you might think it's just one of these streaks coming from the nebula. But actually, this is a background edge-on galaxy. So James Webb is looking through nebulae and seeing galaxies in the background. You can see it even more clearly here. And even through, you can see galaxies. So this turns out to be a galaxy. Behind really dense clouds of gas and dust, which enables all kinds of new science. This, I want to talk about this one in particular because this is the first image that was produced. You might remember this is the SMACS field. This is a cluster of galaxies. So these little, almost really bright ones in the middle here are very heavy galaxies, all very close together, much closer than everything in the background. And their collective mass warps space-time such that the light from the things in the background is bent. And you can see that because the galaxy and all around them are bent in these arcs. And the arcs all sort of surround this center cluster, which is really cool. This is something that general relativity, Einstein's theories predicted 100 years ago. But if you download the high res, there's so many interesting things here. There's this galaxy. It's this one. I don't recall, but there's one they're calling it the Sparkler Galaxy. It's got a ton of popular clusters that you can see, and they're multiply imaged, and it's very cool. This galaxy here, you can see it's actually imaged twice back to back. So very cool. There's this one, which kind of looks like a sombrero sitting on top of another galaxy. But this turned out to be pretty controversial for astronomy, because this is a very nice deep field with lots of really far away galaxies. So many that are really very faint and very red, which to astronomers means they're probably very old. You're probably looking at galaxies right back to the beginning of the universe. So obviously the image dropped in within days. People were putting out papers claiming that they had found the furthest galaxy ever detected. galaxy fully formed 200,000 years after the Big Bang. No, there's plenty of papers coming out now saying really these are just a lot of them are just dusty galaxies. There's a lot of dust obscuring the light from the galaxy, which makes it look older and makes it look further away than it actually is. Some of these things are indeed quite far. There's plenty of them that we can which is incredible. That's still 400, 500,000 years after the Big Bang. Not quite the oldest thing we've ever seen, but it's not changing how we view cosmology, which is a lot of what was coming out early this summer. So that's a little bit of the science as it stands. This is maybe one of the more important things about this thing we're doing. You might not be particularly interested in looking at this because it's just a graph, it's not a big picture. Ignore the planet in the background, that's just part. This is a spectra of an exoplanet as it passes in front of its host star. And what Webb allows us to do is measure the spectra of an exoplanet's atmosphere, which is something we weren't really capable of doing before. We had tried to do it, but what we really get is what kind of looks like over here, where it's just noise. And you can pretend you see something in it. But this is crazy. This is very clear signs of water in the atmosphere of the planet in another solar system, which we think it's a gas planet, so it's probably not harming humans. But water is one of the signs of life that we look for. It's one of the indicators that you might be looking at a habitable system. Because our lives are more or less based on water, 70% water. That's really important. That we're capable of doing this is huge for astronomy. And just recently, another paper came out on. I'll get to that later, but there's more on this topic. I wanted to show this one because some of these things came out much later in the summer. You might not have been tuned into pieces at this point. This is the Tarantula Nebula. It's another early release observation. And I like this one because Halloween's coming up. You can see again, there's these bright stars in the middle. It's blowing the gas and dust out to the edges. This is part of the Orion Nebula, I think. This is a huge area of sky. And the imaging is great, the colors are great. There's great science to do there. But I thought this one was great to really highlight what we can do with integral field movement spectroscopy, which is where we take a spectra, that sort of prism thing, we pick out the elements that are present, for every pixel in an image. So this is an MRS, medium resolution spectrometer MIRI, image of that same area of sky right in the middle there. It's just a big cloud of gas and dust with maybe a bright spot in the middle. Nothing too important. And it doesn't look like a lot of the rest of the image, which is again this kind of streaky red bit with the dust and the stars in the middle. What we can see here is that if you split this up into spectra, I have few images of spectra. You can see that you have your star in the middle here. This is atomic hydrogen, so just hydrogen on its own, a single proton. Just in the center, and then on the outside of this sort of bubble. In the middle, you have molecular hydrogen, which is like H2, it's two protons together, and hydrocarbon dust. And having those things inside the cell, what you're looking at is actually sort of a dense cloud of gas and dust for a protostar that's at the tip of a pillar that's pointing away from us along the line of sight, which is cool because it gives us a sense of the actual morphology of the nebula. It teaches us more about star formation and planet formation. I personally like this one a lot because this is another year that came out showing the Cartwheel galaxy. Now there's all kinds of cool things here. This is a MIRI near-camp composite again. Remember, MIRI is really good at looking at dust. NearCam is really good at looking at stars. You can see the contrast between this galaxy here and this one here. But this one is full of these dust lines. This one doesn't really have it. And that's because this galaxy has been collided with. It has a really interesting look to it because some other galaxies have gone through it. You can see that the result is this big ring of outer stuff, and then this kind of spokes of gas and dust pointing towards the middle, towards this dense nucleus. So it's really cool to look at the dynamics of how galaxies interact with each other and how they move. Interestingly enough, this tiny little dot right here is a supernova. Nice. Supernova is an exploding star. This star exploded in November of last year, right before the telescope launched. So, and it's still very bright, especially in the infrared, which is very dusty. One of the big questions in astronomy is, where does all the dust come from? And there's kind of two camps. One is that, well, the one I'm interested in basically is it supernova that produces dust? Because as a star goes through its life cycle, it generates heavy rare elements, and then it explodes, and all that material goes out into space. It doesn't stay out there, it's destroyed. Where does it really come from? So looking at this in the mid-infrared, it's still so bright in the mid-infrared because of all the dust it's generating. It's a good sign that supernovae are the things caused by the gas and dust. And as you know, the gas and dust is the heavier elements, the stuff that becomes metals, the stuff that becomes which is cool. So we actually have a follow-up proposal to look at this in more detail. This, I love this picture. There's not a whole lot more science I can say about it. This was actually not an ERO picture. This is just a science group whose data is public, who are looking at face-on spirals to look at the gas and dust and how they interact with star formation and the center of the galaxy. And actually, this image was produced by a member of the public who just happened to get his hands on the data from past. And that's one of the really cool things about web is that a lot of the data is public immediately or becomes public eventually. You do your own science. So someone found this and made their own color picture and posted it on Twitter before the scientists even saw it. Okay, so here's this other slide I was talking about before. This is a different exoplanet with the same sort of name. And this is really interesting because we have never ever seen this before. A clear sign of carbon dioxide in the atmosphere of another planet outside our solar system. This is important because our planet has carbon dioxide in the atmosphere. We know that it's part of the life cycle here, it's part of the exchange between aerobic species and plants. We also see it in the atmosphere of Venus. We also see it in the atmosphere of Jupiter in small amounts. So we associate this with processes that could come from life, but it's not a common material because it's a very heavy, complex molecule. So seeing it is actually very difficult. But to see it this clearly in the exoplanet atmosphere is huge for astronomy. So this is a very recent result that you may or may not have seen, but this is very cool. This is a bit what I was talking about earlier, the current state of the science field. This is one of those galaxies that someone claimed was probably the first galaxy ever made in human history. Turns out it's not. The way that people guess, normally what you would do to get the distance to a galaxy like this, or the age of the galaxy, is you would take a spectra and see how elements you know of correspond to how they look in the rest frame here on Earth. So if they're going to be shifted, red shifted. And no matter how much they're shifted, to see how fast it's moving away from you and how old it is. However, there were spectra of these things when the images came out. So you have to estimate the age by looking at just the photometry, just how it looks in the image, how bright it is. And one of the methods to doing that is called dropout, where if you have enough filters, what you have is basically a spectra, it's just really low resolution. And if it drops out, where it drops out tells you, in theory, it tells you where certain continuum features are, like an alpha. And that would indicate some sort of redshift. So when you look at a galaxy like this bright one in the longer wavelengths, and then it kind of fades, and then it's not really in the shorter wavelengths, you say, oh, it dropped out there. That means it's really, really old, really far away. Well, it turns out that there's actually just so much gas and dust at these wavelengths that you can't see it, but it's still there. Which means it's not a redshift of 13 or 20 or whatever. It's actually more like 5, which is less cool, but it's still cool that you can look at it and determine the composition of the galaxy. Galaxy formation as a whole. And there will be more in the realm of cosmology and hypothesis than the real science and stuff. This is actually my work, my personal science work. Again, I mean, for James Webb, I work on the detectors, on calibration, and things like that. The science work is related to supernovae. So around the time that commissioning was coming to a close, I wrote a piece of software that compares the fields of view that Webb had looked at, just to see if any overlapped by chance. Looking for things that might have changed. So when you subtract one from the other, you might see something that wasn't there before. So in this case, I did this with two JWST images, but it's even clearer with the Hubble image. So I can share the Hubble image as well. You can see that this is a JWST image that was taken during commissioning. This is a Hubble image that was taken in 2011. Here's that another JWST image. Before you can see that the new object wasn't there before. When you subtract the two, you can see it very clearly where everything else goes back to zeros, which to us means it probably is a star that exploded in the time in between these two images, which is it was the first supernova ever detected. I'm personally quite proud of it. And we're looking at all sorts of these things going forward, looking for hopefully the furthest ever seen supernova, the very first stars that could have exploded population-free stars, which will tell us a lot about the early universe, how we think when dust start forming, when the stars start exploding, galaxies form, how fast after the Big Bang it always happen. It will tell us a lot about fundamental physics. So these are important questions. And with that, I will take any questions.
Yes. So I have a favorite James Webb image. What is your favorite of all the James Webb images that we have?
It's my favorite James Webb image. I actually really like the Neptune, or is it Uranus? Neptune, I think. Neptune. That's really cool because it's such a far object, and if you look at the wide field, it's just remarkable that you can still see galaxies and stuff in the background, stars in the background, and then this giant glowing sort of looks like a blue ball and has a ring around it. You can see a ring so clearly where you don't normally think about, the further gas giants that have rings, but they do, and it's very easily visible. But I think that image is just fun.
Can you show it to us? Yeah.
Yeah, probably. Yeah, these are the images of it tracking that asteroid impact. That was very cool. And, yeah, so you can scroll around this and see it, right? It's just really cool how their team looks glowing with the rings. This point source here you might think of as a background star, very bright star or something. That's actually one of its moons. It's so big and bright that it's up those diffraction spaces. It's really cool. And in the end, you can see these really thin full images. It's really quite interesting.
That's spiral galaxies. Well, when the infrared imagery comes in, does it how do you get the color into it?
So in the same way that you would take with CCD here on you would put a filter in front of your camera. That way it's only collecting light at a certain wavelength. That wavelength. Optical will correspond to that. We do the same thing. It works the same way with the infrared. We just have a detector filter in front of it. You get a grayscale image. And then in post-processing, you just take those grayscale images and assign colors to them. And you end up seeing things with the colors that we're familiar with, but in truth, it's not things that you can see in your eye. So the colors are a little bit more arbitrary, but they are generally in this correct order. If that makes sense, the longer wavelengths are red, shorter blue, and
And then that's also how you determine what elements you're seeing.
Sort of. The filter itself tells you more what element you're seeing. So, for example, in theory, things that are close by, the 7 micron tells you about all polyaromatic hydrocarbons. It's a kind of dust feature. So if you're looking for that sort of thing, those filters. And the filters are designed to look for specific features at certain distances that are interesting. Take a picture of the black hole. If you need, can take a picture like the ones that were released a few years ago by the Event Horizon Telescope, where it's very clear that there was a black circle in the middle and all the gas and dust around it? The answer is no, because that telescope was a collaboration by telescopes all around the world that were combined in such a way that they mimicked a telescope that was the size of it. James Webb's big, it's not quite that big. However, one of the things it does and really well at are things like the black nuclei, which are big black holes in the center of galaxies. Block those out with photographs and see the dust around them in sort of the same way.
Is there something with the launch of the James Webb Space Telescope, particularly supernova, hoping to find the answer to it?
Yeah, for supernova, one of those questions is the question about dust. Are they producing enough dust to fuel the universe the way that we see? That's not one of my main questions. My main questions are really when did the first supernova happen and what did they look like? Because that tells us a lot about. So when you look at the light curve of the supernova, how the brightness changes over time, the spectra of it, you can infer things about what type of explosion happens. So different types of explosions cause supernova. So one of the big theories is that the very first stars all were huge, primarily almost entirely hydrogen star population. And the thought is that those stars will, when they explode, they would go in what's called air instability supernova, which is inspiring things that happen in the universe. But then there's some theories that you might even be able to get with a type 1A supernova, which is when you have a dead star, a white dwarf, accumulating charge on a flame star. And so much that it reaches limit to explodes. And the question is, how early can that happen? How early can apparent instability happen? That tells us how big the stars were, how fast they weren't. And then lets us infer things about cosmology.
We were fortunate to follow the space shuttle program, and so since we were able to update that, any of the space companies in all aerospace working on missions that give us service to what else.
That is an excellent question. So Webb was not designed with the idea of being able to service it because it's so far away. It's 3 times the distance, more than 1 million miles. And because it's so big and all that, it wasn't designed to be able to service the instruments that replaced them in the same way that Hubble was. And at the time, it was thought that the real limiting factor in the lifetime of the telescope would be its fuel supply. So it's in this orbit out at L2, but we can't go too far, otherwise, if it goes too far, it might fall out of orbit and we can't get it back because we can't turn it around. We only have thrusters on one side. So we keep it from going all the way out to L2, just barely, so that it falls back towards us. And every so often, we have to boost it out again. That costs fuel. The launch was so good that initially it was going to be a 5 to 10 year mission. Now we're looking at a 20 to 25 year mission, probably. So we don't have to do anything to it for the time being. There might be other mechanical failures and things like that that we just simply won't be able to correct. However, at launch time, when the NASA hires Thomas would say, give you a comment that they are already looking into the possibility of mission, a robotic mission to go and attach something to it with more fuel that would enable it to be out there longer. So it's a possibility. It's in the works.
I guess it's related. First of all, thank you for the great presentation. So, Webb telescope is an infrared telescope, which allows capture images from which is awesome. But obviously, science is always moving forward. So, ideally, what's the next advancement in, I'll say, telescope technology that's needed to take this even further?
Excellent question. So there's a couple answers to this. It depends on what you're looking for. For the purposes of cosmology, there's no real reason to go any bigger or deeper than what does in infrared. Because we get just about all the way as close as you can go to the Big Bang when the reionization ended. So that's when things started to actually become opaque and light could actually travel. Before that, everything was such a cloud of gas and dust that you can't actually see anything through it. And that's called the cosmic microwave background. That happens about 300,000 years after the Big Bang. And we can see that using radio observations, which is much longer wavelength. So that you can already see as far back as you can go. However, there are much more. There are other much more pressing questions than things that James Webb won't be able to do. For example, directly imaging the surface of stars or the surface of exoplanets. You can see them with their point sources, or you can see their spectra. You would need a much bigger telescope with a much more intricate sort of aperture in front of it. So one of the ideas, the next generation of the important space telescope is something called CAPEX telescope, something on the order of Hubble size, maybe bigger, or maybe between a James Webb. It sits there, and the star shade isn't actually it's a photograph. The star shade isn't attached to it. It's a separate thing, a million miles away, and they coordinate so that they can block out the light of the star like that. And that way we get super high resolution images. So that's a really interesting concept. The Cable Surveys in astronomy decided that the next big thing they want to build is basically a successor to Hubble and the architecture of James Webb. It's a 6-meter hexagonal mirror, but it's optical. Optical light is much smaller wavelength, much higher resolution. So the things that are much spatially resolved things look even clearer with that. So you can look much more closely at stellar evolution. There is one kind of really crazy concept that, and this is sort of fringe at this point, very difficult, is to use the sun as a gravitational lens. And what that means is the gravity of the sun is warping the light from the stars behind it and magnifying it. So we can, if you send a telescope out and then look back at the sun, block it out, see things from behind the sun and magnify. And it's thought that if you send something into the correct distance, you can directly image and resolve exoplanets. But you have to send the probe way out further than the Voyager probes out, which launched in the 1970s. So it's an extremely difficult concept and it would be very expensive to take a long time. But that sort of thing is probably the future of space. Besides LIGO, LIGO is another mission that's actually works. It's a gravitational wave sensor. LISA is the one that LIGO's on the ground. It's the one that made those gravitational wave detections. LISA is a version of that that's in space. It's a bunch of probes that are all hanging out together to detect gravitational waves in space. And much better than LIGO. So that's in the works. And that's something we do.
So prior to the cable survey, there were discussions that the LUVOIR experiment that you're talking about, the 6-meter optical telescope, might actually be like 15 meters. So have there been rumblings that it's probably going to be 6 meters, or we maybe do?
So there were two designs for LUVOIR. So the LUVOIR again is it's a Hubble-esque. It's a James Webb-esque version of Hubble. There were two designs. There was a 2-meter design and an 8-meter design. Hoping that if you didn't get one, you might get the other. What ended up happening with the fatal survey was the astronomy community decided we could probably still reach the science goal with the 6-meter telescope. And if it did that, it could probably incorporate elements of like CAPEX mission into the same telescope. So I think the plan is everybody's accepted that a 6 meters is probably good enough, and that's what we're going to do. And going for something bigger, you run into sort of budgeting questions where things do. Stick to something smaller that still accomplishes your science goals, and then develop a plan that you don't want to cost you don't want time.
Should we just some of the
cycles, and there's a cycle that lasts every year. So cycle one is full of stuff, it's all publicly available, you can see what they are, there's plenty of things looking at. Cosmology, galaxies form, studies looking for signs of life on exoplanets, planets, those things. Those are the really big questions that Jim goes to answer. And there's always, every cycle, there's a new program to do those things.
Just curious, how much would you cost being able to build?
So the original budget, I believe, was about $1 million, maybe a little less. It ended up being almost $12 million. It was originally supposed to launch in 2007. So it launched in 2022. Very overcost and very over budget. But it was sort of some cost fallacy. You put so much time and money into it, got it finished. Do you mean on board or do you mean analysis? Yeah, so on board, the computer on board James is actually quite small, it's not super powerful. It runs a JavaScript. So we see the little text script that it uses to run its software. And it has a very small hardware component. From the ground, Python, people still use that.
How do you protect the computers on board from like incoming like charged particles or like cosmic rays that might hit transistors and cause false errors? Or...
Yeah, great question. This has been a thing that we've been doing in space for a long time. So the command module is surrounded in sort of that's designed to protect it from as many cosmic rays and things like that as possible.
With that, how are you allowed to communicate with it if you're also protecting it from like outside?
So there's an antenna on it, so it's just like cable that runs the antenna once they're 24/7.
Okay, that doesn't detect it by anything.
No. If it does, then there's definitely redundancies. So it has to just do everything. And it communicates via the two space network. So there's 3 satellites. There's always one that can see it.
So as often, obviously, we've seen pictures of galaxies and stuff like that. Of course, some of our exoplanets. These are big things for the news. This is what the public likes to see. What is James Webb hoping to tell us that maybe scientists are?
Lots of things. There's a whole community of people that just talk to us, how it behaves and how it moves through systems, how that leads to star formation or star death or things like that. Sort of minute questions. They have to do a lot with the dynamics and modeling and things like that. So not things that the public is really interested in. But then questions even in the solar system, like how many things are actually in the Oort cloud, or does the Oort cloud actually exist? It's a question that is somehow still being asked. So, and James Webb can see translate objects extremely well. So that's one of the big questions.
Are there any plans for, so James Webb Space Telescope, because of the fact that it's operating in the infrared part of the spectrum, can much more easily see distant galaxies because of radiation. But are there still any plans for something like that field for James Webb?
Yes. Well, everything is but there is a program at least in December to revisit the bubble sky with Miri for something like 12 hours or something like that, which is comparable to the amount of time that the bubble spent on that portion of sky. And there's a couple other really good details planned as well. You can see these in the proposals. Now I assume there'll be more.
Obviously, building tremendous undertaking. Can you speak at all to the level of international cooperation on the web?
Yes. important to know that this is definitely an international project. It's not just NASA, it's NASA and the European Space Agency and the Canadian Space Agency. So for example, the European Space Agency was responsible for the launch vehicle. That's why they launched on an Ariane 5 and not something like SpaceX. SpaceX didn't really exist in the design. It couldn't be made. But also the Ariane 5 was at the time the only rocket that could actually fit inside. And it's also the most reliable rocket ever. So we did that. The mid-infrared instrument is a collaboration between the United States and the European Consortium. So we've actually designed and built in the UK and tested there, as well as collaborators at the University of Arizona and at JPL in California, as well as obviously at Space Telescope Science. And NIRIS and FGS is the fine guidance sensor. It's sort of a less talked about instrument, it's the thing that tracks the stars, that stuff. That's part of the NIRIS system, which is a collaboration with the Canadian Space Agency. And so they did a lot of the design, engineering, testing of these things before they were delivered to the telescope to be implemented, and then also obviously also helped with the implementation. And then those teams were primarily responsible for commissioning the telescope. So we had European collaborators in for the entirety of the 6 months, so they were constantly doing stuff and analysis for us.
I'm very interested in what you did with the long baseline using Hubble and JWST. And then I correct you, you subtracted the Hubble image from JWST. Sorry. Can you talk about how elaborate that process must have been for finding the objects, getting the same perspective, making sure you're subtracting apples from apples, not apples from birds?
It's a really complicated thing to do. And it's an ongoing project for us to develop this pipeline that does it sort of automatically. This was more of a manual effort, obviously, because it was early on. We had pegged this particular field as something with 2 epochs for JWST, so that would have been an easy subtraction. But because this had already gone off before those 2 fields, there would have been a dimming, but it probably would have been noticeable to the eye. But we did luckily just compare it to Hubble and we saw that it wasn't there. To do a subtraction like that, it's difficult because the filters are different. You're seeing different light, pixels are different, point spread functions are different. And in order to get an honest answer, you have to do a lot of tweaking to those 2 things. You have to match exactly, do a lot of really precise astrometry. About exactly what the sources are and all up, distortion and things like that. You have to resample one of them to match the other one. So James Webb is a lot more high definition than Hubble. So we had to downsample the James Webb images so that they match the Hubble ones, so you can get an honest subtraction. And then doing photometry, which is actually measuring the number of photons you're getting. It's a different process for those 2 instruments. And so making sure that those 2 measurements agreed on a number of stars that were consistent and standard was part of the process as well.
So it's fair to say that what you were showing us was a prototype of a process that you bring value to use on time.
Yeah.
It seems like you got really good waveform sensitivity as well. So that's helps you to actually really model the wavelength dependent point spread function.
Yes, yeah, we have exceptional set models for all the filters.
Is there any information you guys are trying to collect on the solar system, or is it mostly just kind of,
Yeah, actually, so this is not just the RO, this is doing science on this picture. There's definitely science being done with the Jupiter picture. If you remember that. So we've got a sort of unique look at Jupiter to see that it actually happens kind of auroral caps, much like we do here, in certain filters, which is interesting. And seeing more about the rings of Jupiter is also interesting. Counting up things like that. We even looked at Mars, which is kind of so close and so bright, but we did. And we can actually resolve surface features on Mars and see how the elemental abundances on the surface change and try to figure out, where does water flow, where does all the atmosphere stuff located. But more than that, trans-Neptunian objects, things like asteroids, asteroids from outside the solar system that are passing through. Happened a few years ago. So there's definitely a lot of solar system science happening.
Space like that, how do you decide what's north and east?
You choose basically. There's a bunch of coordinate systems that you could be in. This coordinate system is defined basically by Earth, where Earth is pointed. So north is sort of where our north point, our north pole is. This is like pretending you're on the ground.
Right.
So one of the challenges NASA has since inception is explaining to the American taxpayer why it's worth it for the average American to do what that's doing, right? But I'm not a cynic, I'm just asking. So someone's sitting there going, $12 billion. Roads where I live is still a factory, but it's $12 billion in a web telescope.
Yeah.
Apples and oranges, but can you just, in 1 or 2 sentences, explain how the Webb telescope is going to help the average everyday person? Maybe not right now, but in the long run.
In the long run, the things we learn about physics are always useful. Cosmology and particle physics are not so distantly separated when you get down to brass tacks, Big Bang. So learning about those things helps you useful physics, computing or something like that. I don't know. Those things are really nebulous and far out in the future. But projects like this, big projects like this, that are huge collaborations, and they sort of have the technology to do, much like the spatial missions and the ISS, you get derivative technologies along the way. So there were advancements, for example, this is one of the only examples I can remember. There are advancements in optics that are now being used in really high precision surgeries. So it's saving lives, and it's actually saving hospitals money and saving people money and healthcare bills, things like that. So, and there's plenty more of those sorts of things that were a result of the engineering science.
Any other questions? So just to end, I'd just like to say thank you very much for what he also gave us a presentation earlier on today with our current students to show them how to process JWST data in the afternoons. It's actually a really great example of feedbacks of former graduates coming back and helping out our generation of students at student concept, giving them introduced to the real professional astronomical physical community. I'd also like to say thank you all for coming, and let's have a round of applause for Mike. Thank you. Wow.